So I would like to ask the atmosphere people to make room for the subduction people, and as fast and orderly as possible. As you know, chaos is not random. And while you do that, I'll introduce the first speaker of this fragment of our session. And it's an invited talk by Sarah Peniston-Dorland from University of Maryland. And she'll talk about everything that's happening in the subduction factory. And because of the delay, I'll let her start right now. You got your...
I have my pointer. What do I need to do here? This? Okay.
This is just your...
All right, well, we'll continue on the theme of chaos introduced by our atmospheric colleagues and talk about Milan zones. I'm going to be describing a bit about what we've been doing in my research group, investigating processes that are occurring within subduction zones by examining subduction-related metamorphic rocks. And I am going to be talking specifically about subduction-related melange zones. You can see here 3 images that show what melange zones are like. They are essentially larger-scale blocks surrounded by finer-grained melange matrix. And this is automatically advancing itself, which is kind of stressful. But anyway, I'll have to talk fast to keep up with it. Melange zones are thought to represent the interface between the downgoing subducting slab and the overlying mantle wedge. This location is ideal for providing information about processes that are critical to understanding the subduction system as a whole. Processes such as infiltration of fluids, associated mass transfer, and tectonic mixing of crustal and mantle materials. I'm going to be talking today specifically about reaction rinds, and these are features that surround many of these block cores. I'm going to be talking about mafic blocks with these reaction rinds. You know, think of like a lemon rind surrounding a lemon. The rinds themselves have different mineralogy and chemistry, and the differences have been attributed to 2 main processes. One is infiltration of chemically reactive fluids, and this infiltration process is inferred based on large ion lithophile element concentrations and also stable isotope systems like oxygen, boron, and lithium. The other process to which these rinds are attributed is mechanical mixing of material derived from the mafic blocks with peridotite material. And this second mechanism is inferred based on elements that are less mobile in fluids, such as nickel and chromium, and the highly acidophile elements. And the goal of what we're doing now is to try to provide some sort of temporal context for these processes in order to sort of decipher a history of what's going on within these subduction zones. So I'm going to be talking about the Catalina schist. It's a mid-Cretaceous age subduction complex that's exposed off the coast of Los Angeles. I'm going to be talking about reaction rinds from 3 different metamorphic facies. The lowest grade are lawsonite-albite facies, which is indicated on the map, and also the associated PT diagram by the green stars. Next highest grade are lawsonite-bluish facies, which are the blue stars on both diagrams, and then the highest metamorphic facies exposed in the Catalina schist, amphibolite facies, which are indicated by the red stars. And I'll be using those colors on graphs later on. This shows a field photograph of one of these block cores along with its associated rind, garnet amphibolite block core, and actinolite-rich rind. I'm going to start by describing the highest grade, the amphibolite facies rinds. These have been well described in the literature. Serena Sorensen and her colleagues described these in the mid-1980s. Whoops, sorry, it's going too fast again. So the block cores themselves are typically garnet amphibolites. You can see a thin section here on the left. With a nice pale pink garnet porphyroblast surrounded by amphibole. The pie charts that I'll show you are point counting results from representative samples. So you can see about 3/4 amphibole, 20% or so garnet, and then minor amounts of phengite, chlorite, rutile, and other trace phases. When we look at the rind, we also see amphibole, although it's typically more actinolytic in composition. Sheet silicates are more abundant in the rind, so we have quite a bit of phengite, which is a magnesium silica-rich muscovite, and also chlorite. And the sheet silicates and the amphiboles in the rind define a concentric foliation that is essentially wrapping around the block, and that gives us a hint of the dynamic nature of the rind formation process, at least at one point during its history. In some cases, we also see quartz veinlets, like this little vertical feature in the thin section scan on the left. That's parallel to the concentric foliation. And in this particular sample, rind sample, we found resorbed garnets, and this gives us some information. We can compare the garnets from core to rind to try to learn about timing of different events. So I'm going to compare the chemical composition of cores and rinds, and on these graphs, the block cores will all be the darker colored symbols. The associated rinds will be the lighter colored symbols. The matrix is going to be these larger fields outlined in the same color. And then I also have black diamonds showing pyrrolite composition, which is to give us a representation of what primitive mantle or peridotitic compositions would be. And what we see from looking at the whole rock chemical compositions are that the reaction rinds are more peridotite-like. They have higher magnesium and lower aluminum than the block cores, and higher nickel and chromium contents. The highly siderophile elements also suggest that these rinds have a peridotite-like component. Here we see osmium, iridium, ruthenium, platinum, palladium, and rhenium. Their concentrations are normalized to primitive upper mantle. And they're compared to basalt, which is the stippled field, and peridotite compositions, which are the gray field. And you can see that the block cores resemble basalt, which is their presumed protolith, and the rinds have much higher contents, in particular of osmium, iridium, and ruthenium, that are more peridotite-like. When we look at the isotope ratios of osmium 187 to 188, we also see that the isotopic compositions of the rinds are relatively low, 187 to 188, which is consistent with peridotite, whereas the block cores have higher ratios, which are considered consistent with crust. These highly siderophile elements, nickel and chromium, are all elements that are thought to be relatively immobile in fluids. And so we hypothesize that their elevated concentrations might be due to some sort of mechanical mixing of peridotite-like material. So to test that hypothesis, we did some mixing calculations, and we show the results here with 187, 188 osmium versus osmium concentrations, mixing between a peridotite end member and the range of compositions for the mafic cores. These samples that are shown here are samples from the Catalina schist, but also reaction rinds from similar blocks within the Franciscan complex in California and the Samana metamorphic complex in the Dominican Republic. They have similar systematics in these three different subduction complexes. The blue line and the red line show the mixing calculation results for the range of compositions of these block cores. And what you can see that anything that will fall on those lines or in between those lines is consistent with mixing. And so the rind compositions do fall in that range that's predicted by mixing, which suggests that mechanical mixing may be playing a role in the formation of these rinds. And we can predict how much peridotite component there is in the rinds using this model, about 10 to 50% of that peridotite component. If you're interested in highly siderophile elements, please visit Julia Gorman's poster in the poster session tomorrow. Okay, so I mentioned the fact that there's a garnet in the rind. The presence of garnets in both a core and rind allow us to test the relative timing of the chemical changes. And I've got a little thought experiment here to illustrate what I mean. If the chemical changes that formed the rinds occurred before garnet growth, we would expect a chemical difference, here indicated by the pink and green colors, and that the garnets overgrowing that chemical difference would likely be different in their chemical composition. On the other hand, if the garnets grew first and then there was mixing that created the difference in chemical composition, we might expect that the garnets would record the same composition in rind and core. If the chemical change occurred during the garnet growth, we might actually expect some overlapping in composition, in particular in the very centers of garnets. So we looked at the garnets in both the, okay, it's just going to zoom right on by. We looked at garnets in both the block core and the rind, and we have, I show here some X-ray maps. The top two are X-ray maps of a single garnet from the block core, manganese on the left and calcium on the right. And you can see both display nice concentric growth zoning that suggests that they're retaining their, the compositions during garnet growth. All right. And at the bottom here, you can see two X-ray maps of Rind garnets, and they are to scale, so they're much smaller, you can see, and that, I think, tells us something about the history of these blocks. Even when you take into account their resorbed garnets and look at the resorption halos around them, such as, as you can see here, I'm going to have to talk really fast. The yellow line shows that you still have a relatively small size there. But importantly, you can look at the compositions, and maybe you can look at the compositions. You can see that there's a much lower calcium content in the Rind garnet compared to about 5.3 to 5.9 weight% calcium, compared to 6.7 to 12 weight% calcium oxide in the core garnet. We have clearly different chemical compositions in these two populations of garnets, and these differences suggest that the garnets did grow after the rock was chemically altered. All right, so there are reaction rinds in the low-grade rocks, and they have not been reported in the literature, so I wanted to spend a little bit of time describing them. This is kind of early stages in this work, but the mineralogy and chemistry of lawsonite albite and lawsonite blueschist facies rinds are fairly similar, and we see that mineralogically, most of these samples have nice plagioclase phenocrysts that are now composed of albite, lawsonite, and phengite, and then there's also quite a bit of chlorite, which is the dark material surrounding the feldspars in this cross-polarized light image. The rinds are composed of amphibole and chlorite, and like the high-grade blocks, we see a concentric foliation in the low-grade rinds. Chemically, the rinds, the comparison of rind composition to core composition is similar to what we see in high grade. So we've got, again, the filled symbols. The green is lawsonite albite facies. The blue is lawsonite blueschist facies. And you can see that the rinds compositions have higher magnesium and lower aluminum, similar to the high-grade rinds, and also higher nickel and chromium, just like they do at high grade. So we've got similar chemical differences or chemical changes going on during rind formation. One interesting phenomenon that we observed when we looked close up at the contact between blocks and the surrounding melange matrix is that the nature of that contact is really quite complex. It's very convoluted, and bits of rind broken off in the matrix worming its way into pockets within the rind, suggesting that this is a very physical process of shearing and mixing. We see this also on the small scale. Don't let the Sharpie pen deceive you here. The reaction rind is this sort of pale green material. We can see little pieces of it breaking off, and the gray melange matrix is worming its way in between those pieces. Okay, well, when we look at relatively fluid immobile elements, we can see potassium and barium at the high-grade block cores, and block rinds have higher, some of the block rinds show addition of barium and potassium, which is not coming from the surrounding peridotitic matrix, so this is likely due to fluid infiltration. We see this also in lithium, increase in lithium concentration. There's variability in lithium isotopic composition also that may reflect diffusive fractionation of lithium isotopes. The addition of potassium and barium is associated with the mineral phengite. That's the major potassium-barium host. And we see the phengite replacing garnets and amphiboles. And so these replacement textures suggest that the potassium-barium addition is rather late in this process, and random orientations of the phengite suggest that we have this replacement occurring in a more static environment. If you want to learn more about these fluid mobile elements, please visit Natalie Seaver's poster in tomorrow's poster session. All right, so I just want to leave you with a set of schematic diagrams. We're trying to interpret a history of these blocks. You see a nice cross-section here. 1, 2, 3, and 4 on the cross-section correspond to 1, 2, 3, and 4 expanded over here. Early on, relatively low grade, we have pieces of mafic blocks breaking off, mixing with the surrounding peridotite, forming a concentric foliation in this shearing environment. Increased pressure and temperature, we have early garnet growth in the block cores, more breaking and mixing, sort of breaking and mixing and recrystallization. Step 3, continued garnet growth in the block cores, and at this point we might have initiation of the garnet growth in the chemically different rinds. And then very late stage fluid infiltration, adding potassium and barium, and altering the rinds in a more static environment. Thanks for your attention.
Okay, thank you very much. Are there any questions? No questions at all? In that case, are we? Then we'll try and prepare for our next speaker, which is Paige, down here. We'll be talking about an oxygen isotope record of prograde and retrograde subduction fluids preserved in garnets from eclogite and related rocks from California and Greece.
That's like the end. I'm going to work backwards. I hope that's not going to mess anyone up. Thanks very much. Following on Sarah's presentation, what I'm going to try to do today is talk to you a little bit about how oxygen isotopes in garnets experience some of the same processes that Sarah's been talking about. How do I make it go? Sorry. Okay, thank you. So I'm sure I might be preaching to the choir on these two, so I'll move pretty quickly. But why oxygen isotopes? Well, as well known, oxygen isotope ratios are powerful tracers of fluid flow, fluid fluxes, even in some cases the sources of the fluids. And in particular, in situ analysis of oxygen isotopes can help add a relative timing component to metasomatic events that might be recorded by the oxygen isotopes. But a caution here, especially in rocks like eclogites and other metamorphic rocks, is that mineral scale studies in these lithologies have shown very limited variability. This is in part because they tend to be very well equilibrated, and there's very limited fractionation between garnet and the other mafic phases that make up the rock. Why garnets? Well, this is really probably preaching to the choir, but as we've seen, they grow through subduction and sometimes during exhumation, and clearly, as Sarah showed, sometimes during these rind forming processes. And in particular, garnet has such sluggish diffusion rates that it can preserve additional isotopic compositions, especially at the relatively low temperatures in subduction zones. And then finally, garnet, because it is of such utility in thermobarometry and geochronology, can potentially allow us, especially if we analyze the isotopes in situ, to tie a fluid history of the rock to a tectonic history of the rock. This year, Russell et al. Published a paper in contributions on oxygen isotope zoning in garnets from orogenic eclogites. So this is a subset of their data, and here across the top we have three core to rim cation traverses of garnets that show prograde zoning and formed in a collisional environment. And then here on the bottom we have three traverses of oxygen isotopes by ion microprobe that shows a consistent core to rim increase on the order of 1 per mil in general, and sometimes up to 2 and 3 per mil. And this is interpreted as late stage, prograde infiltration of fluids during the subduction or the collision event. So what I'd like to do today is look at the oxygen isotope records preserved in garnets from melange-hosted rocks of this nature. So we're going to look at in three locations. And the first one here is, of course, the famous locality in Syros. So here we have melange-hosted blue schists and eclogites. There's field evidence of fluid metasomatism in the form of rinds. However, mineral-scale oxygen isotope studies by Putlitz et al. Show that evidence of equilibrium between the phases, and no evidence of fluid flow penetrating into the cores of the blocks from the surrounding melange. So here's a backscattered electron image of one of these garnets. This is a pretty ratty looking one, I apologize. But it has some evidence of some zoning in the form of inclusions with a core and a rim. Got to squint though. And then we move on to traverse here, so this is cations. So in this case, I'm showing rim core to rim traverses, and here we can see that it's kind of a classic prograde manganese zoning profile. I'm going to superimpose on this the oxygen isotope zoning, and it's on the same scale here, and it's very, very flat and monotonous. I'm not really cheating, making it look more monotonous than it is by compressing the scale. All of these points are equivalent with an analytical error. So we have a record by looking closely at the garnet. We see that in this case, the mineral laser fluorination data really is an accurate record that the oxygen isotopes did not penetrate into the eclogite. On the other hand, we can come to another melange formation that's closer here, the Franciscan, that we are ourselves blocks within it right now. There is, again, lots of evidence for fluid metasomatism in the form of rinds. Here's one on an eclogite block. But contrary to what we find in Greece, there's profound mineral scale oxygen isotopic disequilibrium between the garnets and the pyroxenes and other minerals in the block. So a little bit of a different thing. So if we look at a backscattered electron image of one of these garnets, this is from the Junction School eclogite, which is just north of here in Healdsburg. This is a high contrast backscattered electron image. And you can see that in the core, which has lots of inclusions, there's maybe some faint zoning, but it gets really dramatic around the edges here. So evidence of embayments and resorption, regrowth with different compositions here, and then even hints of oscillatory zoning here in the edges. So we did traverse across this garnet. And here we have a core rim traverse here. And you can see in the core section of the garnet, again, kind of classic prograde zoning. And then really it's in the outermost 50 or 100 microns that all the craziness happens with the cations. The oxygen isotopes here are shown in yellow with a different scale off to this side. And we can see, first of all, that in the core, it really actually behaves very similarly to the eclogite from Syros. There's maybe a little bit more scatter, but still that's not resolvable within analytical uncertainty. It's only the very outermost data points that jump up by about 2.5 per mil, which is really quite dramatic in an eclogite garnet. Just zooming in here on the 5 outermost points on this side here, I've highlighted them in yellow. The white ones would have been great, but I hit inclusions there, so I had to exclude the data. See, in the outermost part of the garnet interior, my battery has gone out. We all have to go home now. We can see that there are two points, there we go, that are also 4.5 per mil here from the core. And hey, thanks, Sarah. And then, I'm shooting myself, excellent. And then as we move out past this embayment and resorption in the high average atomic number iron-rich zone here, we have 2 more points, and they're also 4.5 per mil. So this garnet has seen a lot, but in the first part of its resorption and then later regrowth, there's no signal from the oxygen isotopes of an external fluid coming in and changing the composition of the rock. Only in this outermost 10 to 20 micron intermediate Z zone right here do we see this jump. I did some work earlier on this rock looking at the inclusions, doing thermobarometry between the inclusions and the garnet, and here this lets us tie some of this data to the tectonic history. The peak pressures and temperatures here from this rock are found in the outermost portion of the core zone, so that's 22 kilobars of eclogite. Then the resorption, and then this outer zone, not the outermost zone, but the bright zone right here, crystallized at 14 kilobars. So we have substantial exhumation before the garnet started to regrow, but still the fluid event happened after that. Moving on to, so we have a record of nothing. We have a record of nothing in the prograde, followed by some craziness during the exhumation. And here we've seen this before. Now we're going to go to Catalina and look at a couple of blocks in the Catalina melange. So first, Garnet hornblende block, similar to the ones that Sarah was talking about, but not looking at the rinds, just looking at the cores of the block. Here's a garnet there. I'm going to start speeding up my talking. And then between A and A, we did a traverse, and we can see that the garnet has, again, sort of typical zoning patterns of a prograde zonation. And then we look at the oxygen isotopes, and we see here that, again, it's sort of the Syros story all over again, or the story of the core of the Franciscan garnet, that this block was in a melange zone that's famous for kilometer scale homogenization of isotopes within the matrix itself, but none of it is penetrating into the core. That's the little gray blob. Well, now we have some of the little brown stringers. So here is a metasedimentary rock that's in the same high-grade melange zone on Catalina. It's a metaquartzite that's got quartz, garnet, hornblende, a little bit of biotite, and rutile in it. These blocks do not have, or I have not found any visible rinds on them. And unlike the I skipped over a bit on the last part, but everything is equilibrated in the Garnet hornblende rocks that don't have the zoning. In these, they have some really profound disequilibrium. The garnets in this block are 18 per mil, and the quartz with variability, this is by laser, and then the quartz is 13 per mil. So in equilibrium, the quartz should always be higher than the garnet. So something serious has happened within the block. The little sugary pink garnets are really pretty featureless with a few rutile inclusions in them, although you can see this is a really high contrast BSE image. You can see some faint hinting of sort of concentric zoning in here. But the cation zoning is really quite mild. Maybe the grossular picks up a little bit at the edge there. But now if we superimpose on the same scale the oxygen isotope zoning, we have a really dramatic zoning profile. The cores of these garnets are 25 per mil, which is kind of extraordinary. And then the rims are 10 per mil. So the quartz, again, is at about 13. So the rims of these garnets could actually be in equilibrium with the quartz. The cores are very flat, but then sort of jump down in a step to about 18 per mil, and then drop further down. If we look at another garnet from the same rock, this time I'm just using the whole scale. This is a much larger, about a 3 millimeter garnet. We see more scatter, but again, a core of 25 per mil, and the rims of 10 per mil. And in this case, on one side of the garnet, we really stay right up at 25 until it does a marked jump down to 18 and then down to 10. And this side, it slopes a little bit. We actually see something similar in zircons from this rock. So this is a zircon with a detrital core. The detrital cores have old ages and are 6 to 7 per mil, which is a pretty typical value. There's sort of this chaotic zoning in this CL image. And then in this mantle region, the oxygen isotopes show 24 per mil, which is also really quite striking for a zircon and is in equilibrium with the garnet cores. And you don't see the data point here, but this outer gray rim right here is right at about 18 per mil, which matches. So I think what we're seeing here is a block in the same melange zone as the mafic blocks, but unlike these blocks, whether in the melange or before they were incorporated into melange, they saw a tremendous amount of fluid flow going through them. The quartz, which is easily reset, probably started out with a very high bulk composition. Maybe the protolith was a silicious ooze. And then as the fluid moved and the garnets and the zircons grew, only the slow diffusion of the garnet and the zircon were able to sample the oxygen isotope environment while the rest of the rock was reset. So just a quick summary. We can see that garnet can record various fluid histories during subduction and exhumation, and that for mafic blocks, this fluid history, at least in the prograde, is pretty monotonous. It seems like the fluid sources are either within the garnet but there's no fluid at all. Only during certain late exhumation features we've seen in this limited sample set can you get some dramatic changes. Metaquartzites, however, record a changing fluid environment during growth. Now, maybe this is because of a difference in permeability, and they had that fluid in the same melange zone, or perhaps there's a tectonic difference. And so I further work on inclusions to try to establish pressure temperature conditions for both of those rocks, I think is indicated. And I hope I've demonstrated that in some cases it can be a powerful tool to link fluid and tectonic histories. Thanks very much.
Any questions? Yes. It's up to you.
Hi. I'm sorry, where? I didn't hear the first part. Which of the places?
There are some very garnet zones which claim that they've shown fluid pathways.
No, I didn't. But I think it's entirely possible that by working across them and looking at variability in the texture, I think the big indicator though may not be in the cation zoning of the garnets, but is in disequilibrium between the garnet and the host, and that might be true within these the localized channels. But I haven't seen that yet. Yes. Well, I mean, I'm sorry. Oh, I'm sorry. Thank you. Yes, I will repeat the question. Could those profiles, the really dramatic profiles in the quartzite, be caused by diffusion? I would tend to say no, just because those profiles are so steep. They're so big and they're so steep that if was diffusion, then I think are you referring to the relaxed side or the steep? There was a steep side. I don't think you can make that by diffusion. On the relaxed side, maybe, but why only on half the garnet and in a rock that probably wasn't that hot? So I'm inclined to say no. Yes, sir. Yeah, I'm sorry if I didn't make that clear. I think the quartzite is recording a primary growth feature. And I mean, I suppose this is also doing that, but only after a period of resorption. So I think we have multiple episodes actually of growth, resorption, growth. There's another small resorption band in there that's hard to see. So I think that's happening on the Franciscan, but in the Catalina one so far, everything is so homogeneous generally except for the oxygen isotopes that I think that, now whether it's a continuous tape recorder that the Garnet was growing all the time and it's recording fluid pulses, or whether the fluid was flowing all the time and the Garnet was turning on and off, I don't know. Please. Sorry, me. Well, I want to caution you in using the term of the replacement, because I think because these diffusion rates are so slow in Garnet, especially at these temperatures, that I think that the Garnet is sampling growth, and that we're not seeing the fluid go in. Or is it Garnet 1 grew and then dissolved, and then later on in the PT path, Garnet 2 grew? That's our interpretation.
I think
I'm
you need
sorry.
to continue
Yes.
the discussion over a beer later on.
Thanks.
We will move on to our next speaker, who's Mark Keddick, who worked with Ethan Baxter on Garnet growth as a proxy of progressive dehydration in subduction zones.
Okay, thanks. Okay, so we've just heard about Garnet recording fluid histories, and I'm going to talk about Garnet recording fluid production in subduction zones. We've heard a lot in the last few days and in the last few years about the significance of dehydration in subducted lithologies, particularly for returning volatiles to the deep mantle, for arc magmagenesis, for subduction zone seismicity, and for a bunch of other processes. And the interest in this has led to a lot of work, and it's led to rather classic papers like this from Kerrick and Connolly, who tried to decipher when, in pressure temperature space, fluids would be produced during subduction zones. And so here we see a map of stable mineral assemblage for a hydrated morb composition. And from that, they inferred, it might be a little bit difficult to see here, the amount of residual water that would be left in this rock as it traversed through pressure temperature space. And this leads us to a rather simple problem, and the talk today is going to be a rather simple talk, a rather postulate a simple hypothesis. The production of fluids, unfortunately, is generally difficult to reconstruct from preserved rocks. Generally speaking, once the fluid's produced and it's free to leave the rock, we have very little evidence of its production. And specifically, the source and the timing of water release is very difficult to pinpoint unless we can find a passive marker that in the dehydrated rock residue that can somehow be linked to this dehydration. And so if we look at these images here, these are partially dehydrated rocks. There's certainly still a lot of hydrogen left in them. This is a garnet blue schist from Syros. And is there evidence in these rocks for partial dehydration sometime back in their history? Or is there no way of finding out about their precursor dehydration histories. And what we're going to postulate today is very simply that there's a very strong link between garnet growth in these rocks and dehydration reactions. So the dehydration reactions that are producing the fluids are also producing a significant amount of garnet. This is not a new idea, of course, and it's really neatly shown here in this compilation by Brad Hacker and colleagues, where the amount of water left in samples that were estimated to have equilibrated at specific PT conditions, the amount of water here that's left in them is shown in red. And we can see that it decreases from low pressure and temperature to high pressure and temperature, and that it decreases rather dramatically at the points at which we would first expect garnet to become stable. And of course, if we were to choose a mineral that we would want to use as a proxy for dehydration, garnet might be that mineral. We've just heard in the previous talk a series of reasons why garnet would be useful. Not least, we can use it as, in thermobrometry to estimate the pressure and temperature of its growth, and therefore the pressure and temperature of dehydration. There's a mounting body of work that suggests that we can now not only take bulk crystal ages from these garnets, but maybe quarter rim growth ring ages to know the duration of garnet growth. And therefore, if garnet growth is strongly coupled to dehydration, the duration of this fluid production. And so the very simple questions that I want to ask today are, how well correlated is garnet growth with fluid production? Or if I turn that question on its head, what proportion of the fluid that's produced during progressive subduction is correlated with garnet growth? Can we quantify this number readily? And if so, how sensitive is this to the specifics of the subduction PT path and the specifics of the rock that we're looking at? To do this, I'm going to show you results from a couple of generalized bog rock compositions. I'll take a hydrothermally altered morb, the same one that Conley and Kerrick looked at, and I'll look at an average pelitic rock. We could look at other compositions, rock compositions too. I'm going to do some simple thermodynamic modeling for those compositions. Importantly, these calculations are stepwise along a PT prograde history. And at each step, I'm going to take out any fluid that was previously made, and I'm going to extract that from the rock. I'm not going to subsequently rehydrate the rock. I'm not going to consider infiltration of fluids back into the rock. I'm just going to progressively fractionate away fluid. I'm also going to fractionate away garnet. I'm going to assume, as we heard just, that the diffusion rates in garnet are slow, and that once it's produced, it's essentially extracted from the rock. It can no longer back react with that rock in a simple fashion. That, of course, means that the results are path dependent, and so we can't use a similar approach to Kerrick and Conley. These fractionation steps are actually rather important, and I'm not going to get probably time to show you the difference of considering them or not today. There's ample evidence in the literature to suggest that we need to consider these, not least from Matthias Conrad-Schmolke, who I see sitting back there. But we need PT paths, and I'm going to show you examples from 3 paths: a cold one, an intermediate one, and this very hot path here from top of the subducting slab geotherms from Syracuse et al. And what we do is we discretize these paths into a series of nodes, and we perform the Gibbs free energy minimizations there. Important point here is that I'm considering fluid to be a pure water CO2 binary, and I'm aware that there are implications of this because we don't allow the water to take with it as it leaves any dissolved load. Here are some results, or rather here will be some results in a moment. For the morb composition and for the P-light composition, we'll have progress, so temperature along the x-axis, pressure along the x-axis here. Also, you'll notice that the PT path is non-linear. It has a rather cool early subduction, then a heating phase, which is almost isobaric, and then another steep compressional part. And I'm going to show in blue the amount of residual water left in this rock, and I'm going to show in red the amount of garnet that's produced. And with a bit of luck, this will work. Yep. So we see, as we progress along the PT path, we're dehydrating, we're losing water from the rock as we're growing garnet. And we can essentially put these results for the morb and the P-light into 2 or 3 domains. There's an early domain where dehydration of the rock is not associated with garnet growth in any way. There's a later stage, particularly clear in the Morb, where there's a later stage, recall this is at very high pressure, of garnet growth which is not really associated with dehydration, where then there's this very strong coupling zone in the middle, which is actually generally associated with this part of the path here. This is for the intermediate temperature path. There's a very strong coupling here in both the Morb and in the peelite. So a significant proportion of the dehydration here is associated with garnet growth. Now, of course, the calculations, I'm showing you water and garnet, but they involve many other phases, and so we can take those phases and we can plot them up. I'll show, this is for the Morb here, and I'll just concentrate on this coupling zone here. This is the amount of the other phases that are present in the rock at that point in time. And so we can use this information and put it back onto here to say what phases are dehydrating and contributing to both fluid production and garnet production, and what are the actual ratio of water production to garnet production during this band. It's a little difficult to see here. There's a light grey band, a dark grey band, and a light grey band. And so what I show here is these numbers are the weight % water liberated per volume proportion garnet grown along that path, and they average out to about 0.52 here, between here and here. And these black bars show the dominant hydrous phases that are breaking down to give both the water and to give the garnet. I can do a similar thing if I move back to the peelite again here. And we see there's about, this number's, well, on average, about half, this number's about half of this number here. So the weight % water per volume % garnet in the peelite is about half of that in the Morb. Recall that I'm taking a very strongly hydrated starting composition in both cases. But this ratio of approximately half is actually true of each of the three subduction geotherms that we could look at. We've just seen results from here. This is the cooler PT path, and this is a much hotter PT path. And we see that in both cases, the average number of about 0.52, 0.26, 0.52, 0.24, and in the hotter case, we see that the ratio is smaller, but it's still about half going from here to here. We can draw some more conclusions from this. Clearly, there's a strong coupling between garnet growth and dehydration in these samples. But the correlation is much weaker in this case in the right, primarily because lawsonite is not stable. I guess you cannot see here. This little band here says lawsonite, this says lawsonite, and this says lawsonite. The cold paths are breaking down lawsonite to grow garnet. The hot path is not. And so we can actually have a look, if we focus back on this case here, for what's the actual source of most of this fluid. And so here we see the moles of water per 100 kilograms of rock and where it's sourced from across this bold line here is this curve here. And we see that overwhelmingly the source of this fluid is from lawsonite. And so if lawsonite's breaking down to form garnet, we see a much stronger relationship here than if it's not. But the correlation's similar in all cases. It's strongest above about 540 degrees C, and above about 3 to 3.5 GPa, essentially the processes become decoupled, primarily because all of the water in both cases, in both compositions by this point, is in phengite, which is stable to out of the right of this model, out of the side of this model. Some more interpretations. Although the ratio depends strongly on rock composition, even going all the way from a Morb to a peelite, actually the difference in these ratios is never more than about a factor of 4. And we've done some more sensitivity testing on other variations in Morb composition, variations in peelite composition, and these results are relatively robust. It turns out that very small changes in the bulk composition of, say, potassium are very important, but moderately large changes in the bulk composition, say the iron-magnesium ratio, don't make a really substantial difference. Of course, input of less hydrated protoliths will predictably lower these ratios, but what it will also do is it will change the P and T at which garnet first grows, and therefore the composition of that garnet growth. And so if we're inputting less hydrated protoliths, we should be able to see that in results. I show here This is the Morb case again, and this is the composition of garnet that would grow at each point along there. This would be the garnet rim composition, if you like. And we can see that it changes dramatically over the first few tens of degrees of growth. And then we can use this, of course, to track in natural samples where in P&T space they're growing, as Dragovic and others did earlier this year, where this point here represents a core composition of natural garnets from a sample in Sifnos. This here represents a composition or a point in PT space for equilibration of a rim composition of garnet. And they use this to construct a heating path. Of course, being in Ethan Baxter's lab, the next thing that they did is they went and they tried to date those garnets from core to rim, and they decipher then a rather rapid, less than 1 million year heating from here to here. And so if we couple that with the dehydration fluxes that we can calculate with these methods, I think we have a potentially powerful way of using garnet and correlating garnet with amount of dehydration. Almost done. Of course, we're aware there are limitations to the modelling here. Some of the limitations would be there's a lack of melting, and so for the very high pressure, the high temperature path, this could be important. And we're using a pure water CO2 binary fluid, and certainly at high pressures and high temperatures, this could be a problem. We're assuming we're assuming equilibration of the assemblage at low temperature and no overstepping of reactions. At very low temperature, this could be a problem. And of course, we're reliant on thermodynamic properties over a very large pressure and temperature range. But the modelling limitations, I don't think, really detract from the key conclusions, which are garnet and fluid production are clearly very, very strongly coupled for the major phases of dehydration in both rocks that we've been looking at. And that garnet, if you like, or garnet growth is a witness to dehydration of really, or production of a really substantial amount of fluid in those calculations. The correlation is strongest in a relatively narrow pressure range associated with a large amount of heating. And although, as I've said before, although the composition, the ratio is strongly bulk composition dependent, it only ranges relatively small between two really rather distinct starting bulk compositions. Which brings us to the final conclusion. I think garnet abundance, its modelled pressure temperature range of growth, and its growth chronology, particularly being able to date from core to rim of when that garnet grew. Maybe we can begin more and more to integrate this as a really powerful proxy for prograde dehydration. What pressure does it occur? What temperature does it occur? And over what duration does it occur within any subduction setting? Thank you.
Okay, we have time for one quick question. Hans?
Do you have an idea how fluorine perhaps would modify your system? There are some garnets which, for example, have 2 to 3 weight percent fluorine.
Off the top of my... sorry. Sorry? The question was, do I have any idea how fluorine would change the system? The easy answer, the simple answer is no. Not least because it's difficult to incorporate into the current thermodynamic calculations. Fluorine's one of several elements that would be interesting to look at in the future. But clearly, right now, we're limited with the thermodynamic constraints that we have available.
Thank you, Mark. Then we'll move on to our final talk of this afternoon, which is by Ivan Savos. And it's links between shallow slab dehydration, mantle wedge serpentinization, and arc volcanism insights from the Izu-Bonin-Marianas.
Okay, so I will take you on a journey to the Izu-Bonin-Marianas. It's a place that I keep revisiting because of a simple reason. It's fantastic for modeling the fate of slabs and fluids in subduction zones, mostly because it's quite away from continental land masses, so we can clearly see what's happening in depth. So here is a bathymetry map of the Marianas, where we can see the Marianas Trench, the deepest trench on the planet, we can see this chain here, which constitutes the volcanic front in the Marianas. These are all islands that are volcanic in origin. And in between the trench and the volcanic front, we have these unique mud volcanoes that erupt serpentinite. So they are located about 80 kilometers from the Marianas Trench and about 120 kilometers away from the volcanic front. So they are in a medium position, which allow us to see what is happening between the time that the slabs begin to subduct and the volcanism that occurs in the arc. This is just to give you a perspective of the volumes that are erupted at these mud volcanoes. We currently believe that these are due to highly fractured forearc basement, which allows the propagation of hydrated mantle wedge, which rises buoyantly all the way from the subducting slab to the surface. And they are quite large. This scale here is 5 kilometers, so they are, if you think of modern, well-known volcanoes, the size of Mount St. Helens. And they're also currently active. There is ROV dives at the summit areas of both South Chamorro and conical seamounts that have observed brucite and carbonate chimneys. Also, there is what appears to be an active mud flows that are on the flanks, and they are made of serpentine. Now, we have samples that are from leg 195 and leg 125 of the ocean drilling program. And when the samples come on board, they actually look like this. These are what we call Frankenstein veins, but in general, the point I want to make is that these are highly recording high water rock interaction. There is a lot of veining patterns and a lot of serpentine in the form of a clasts, what we call clasts here. But importantly, these clasts are actually surrounded by blue in color muds that are made of 90% serpentine, but a lot of this material is actually blue schists. So we've recovered a lot of blue schists that are direct samples from the subducting slab, the subducting Pacific slab. Most of these are Harzburgites, mostly olivine and OPX dominated. Plagioclase is always absent, and CPX is very rare. So by all means, these are samples from the mantle wedge. They're very depleted. And when they're hydrated, the fluid that's fluxed through them is with slab origin, which I'll show you in the next few slides. So if you look here on the top, this is a fairly fresh sample of one of these depleted Harzburgites. What we have is a fresh orthopyroxene, olivine. We have spinel and a few grains of CPX. With more advanced hydration, what we see is we start forming serpentine halos surrounding the olivines. We have typical hourglass textures with the mesh windows where we have olivine surrounded by mostly chrysotile and lizardite, the low temperature serpentine variety, and then at some point we actually have cross-cutting relationship. This is a zoom in into one of these Frankenstein type veins that have at least 2 generations of serpentine and probably record high water rock ratios. Now, why is this important? Well, we can look at textures and we can look at the geochemistry of the rocks and try to link these two. Because the protolith is very depleted and we are adding fluid to it, I have chosen here to show you the systematics of boron and the abundances of boron over depth. Boron is a very good tracer for fluids because it's highly fluid mobile. It's also a very temperature sensitive element. But most importantly, boron is extremely depleted in the mantle. Basically, the mantle has no boron. So any addition of boron to the mantle will have a subduction assemblage origin. So as a result of that, most arc lavas are enriched, on average about 10 ppm. The variation is between 5 and 20 at various arcs. But most arc lavas are enriched in boron. And what's interesting is that as the arc lavas, so are the serpentinite clasts and the serpentinite muds that are erupting in the forearc. They have arc-like signature. So that raises the question of potential links between these two sources. So here I show 2 vertical profiles. One is for South Chamorro. This is the southernmost drilled seamount, and this is for conical seamount, which is about 600 kilometers to the north. And we see exactly the same story, which actually is significant, that the two different drill holes, we see exactly the same enrichment patterns and textures. So probably this makes the process a little more global than we first thought. But the point here that I want to make is that relative to seawater, which is the gray triangle here, both in the clasts, which are blue, and in the muds, which are red, we have enormous orders of magnitude enrichments of the element boron. And this is valid for the more superficial samples, but also for the deep samples. So we have a good record that a fluid mobile element should be enriching the Harzburgites, and we see this texturally and we see geochemically. So it appears that boron is a good tracer. Now, what is the source of this boron? As I said earlier, we have a unique position that these serpentinized Harzburgites are actually encrusted, surrounded, flowing in a matrix that contains blue schists. So this is the research of Sonja Pabst, published in American Mineralogist and Lithos recently, where we actually use a time-of-flight SIMS instrument to map the elements boron and lithium. Here shown lithium with red, boron with green, and here lithium with red and boron with green. And what we can see that some of these samples that are actually extracted from the serpentine muds that are blue schists contain minerals phengite, amphibo, and chloride. And what we can see is that, in fact, boron resides mostly in phengites and some resides in a chloride. Here is some heterogeneous distribution of boron in chloride. So we actually have evidence for the host of boron. These are pieces of the subducting slab that do contain boron, but it's quite heterogeneous. Lithium also resides in the phengite and chloride, and interestingly, none of these elements reside in the amphibo. At 4 arc depths, probably amphibos are depleted in this. To move forward, let's use the same method, the TOF-SIMS elemental maps, and show how boron and lithium reside in one of these serpentinites. So this is a combined boron and lithium map. This is the sum of these two maps. So here is the boron map. It actually shows that everywhere we have boron, we have serpentine. And it shows also that lithium tends to prefer the wall rock of mostly veins of chrysotile. So these two elements decouple. But the point is that where we have actually olivine, we don't have any boron. Where we have serpentine, it looks like it's a very nice host for boron. This is just another example. Here we have OH with blue, which marks the serpentine. And here is the same thin section with the same scale of about 100 micron, and we see that boron resides exactly where the serpentine is, and it's very different than these olivine mesh windows. So with this, we move forward to actually say, well, we have all the n members in the equation. We have pieces of the slab, we have pieces of what the slab is dehydrating into. So how this will look, and what is the source of these enrichments of boron? Could it be seawater trapped in a pore space and just dehydrating, or this boron is actually a metamorphic dehydration product that is a reaction on the slab? So we have many examples. I have also lithium isotope profiles and osmium, but I think these two demonstrate very clearly. This is the abundances of the 11 boron, so these are the boron isotopes, and this is the radiogenic isotopes of strontium, also shown with depth. And what we see here is that relative to the depleted mantle values for these elements shown with dashed line, and over here as well, we have a dramatic enrichments and fractionations, both in the sense of boron isotopes, in the muds, in the schists, the pore fluids, and so on, but they differ dramatically from the seawater, which is a green triangle here. When it comes to strontium isotopes, here is again seawater, here is the depleted mantle where things should be, and here are several selected samples from leg 125 to the north and leg 195 to the south. Most importantly, it looks like if we plot the abundances of IBM, the Izu-Bonin-Marianas samples from the volcanic front, they tend to plot in between these two. Again, sort of saying there could be a genetic relationship. Can we somehow trace that? So the first step to do this modeling is to start making plots of metamorphic rocks and arc rocks on the same PT space and the same element-element space and isotope-isotope space. This is something that we very rarely see. So here is some example of what I think is happening in the 4-arc depths. These are all the minerals that are analyzed by Pabst et al., where we can actually see that all of these metamorphic minerals from the blue schists record conditions that are very heterogeneous in boron, so various water-rock ratios and additions of fluid from the subducting slab to the mantle. This addition of mostly heavy fluid leaving the slab leaves a residue that is very negative. So it has -6 plus -4 per mil boron isotopes. If we look at these combined plots where we actually plot the arcs and we plot the serpentine muds and the blue schists in one, what we can see is that there is some problem. The problem is that under the arc, the fluid leaving the subducting slab assemblage, this is outer oceanic crust, this is sediments, and this is the modeled fluid. The fluid should be fairly light. It should be around +1, and it should have variable but overall high boron content. These here are various arcs. This is South Sandwich, this is Izu, this is Marianas and Tonga and Mexico. And what I've also plotted is the abundances of the muds and the abundances of the clasts. This is the boron isotopes, and this is niobium boron. Niobium boron is a ratio that is not disturbed by any magmatic process, so it's a very good fluid tracer, since niobium is fluid immobile and boron is highly fluid mobile element. So what we see is that, in fact, all of this fluid added to the mantle cannot reproduce any of these very high enrichments of several arcs that are intraoceanic, non-crustally derived melts. In fact, if we involve some of these really high and heavy in boron-11 samples from the peridotites that are hydrated in the 4 arcs, that will actually help us explain a lot of the arc samples here. And in fact, all of these muds that contain pretty much melange rocks, mixtures of serpentinites and blue schists, plot exactly where the samples from the Mariana arc plot. So I accept this as evidence from the light element boron, which is a good fluid tracer for involvement of arc material that is heterogeneous in origin, created in the 4 arc, but also from the slab. And here are a couple more examples from the systematics of platinum group elements. These are osmium to rhenium. These are here samples from the South Chamorro serpentinites, the same that I showed you earlier for the boron. And here are some samples from classical boninites from the same arc, which are believed to erupt. These are high magnesium andesites, if you will, erupting early in the history, but associated with arc volcanism only. So we see here a very good genetic relationship where the so-called IPGs are not fractionating very much, but it is suggesting that some of these depletions that we see in platinum and palladium are mimicked in the boninites that are erupting from the same arc. Now, if we look at the systematics of the back arc site, this is the research done by Chris Dale's group, we see the same variable platinum-palladium abundances that are not recorded in the morphs erupted globally. So we have some incredible depletions in palladium and enrichments in platinum. This is this little kick here. Here are the IBM 4-arc serpentinites, and as you can see, they have also the same unique signature, depletions in palladium relative to platinum. And if we actually do a plot of chondrite normalized platinum palladium with osmium iridium, what we can see is that we have a fairly good match. So what I'm suggesting with the boron isotope data is that there clearly is involvement of 4-arc modified serpentinites into the arc sources, the sources of arc volcanoes, especially the Marianas. But this also suggests that there may be involvement of 4-arc serpentinites all the way to the back arc site of the volcanoes. And I'll leave, this is the last slide where I can actually show how I envision that this is happening. This is a common cross-section of a subduction zone where we have serpentine in green. And I believe that this serpentine is actually not staying in the fore-arc, but it is being dragged down to reach arc source depth. And recent PGE and osmium isotope data shows that maybe reaching even the back arc side. So I think further studies should be done about this process of transfer, not really questioning whether it occurs, but there should be a lot of research on this particular part of the subduction factory. Thank you.
Thank you very much, Ivan. I propose that people who want to ask him questions do so over a beer right afterwards. I have two important things to say. Well, a couple actually. Thank you very much for staying on so long. I'd like to emphasize that it's not our speakers who made it so late. We're only 3 minutes over, more over than we were when we started. So thanks for that. The two important things are that we continue this session tomorrow morning at 8 o'clock next door in room 103 with another 4 very nice subduction zone talks. And then tomorrow afternoon we'll have posters in session V43C in the 2800s to the right of there. So we hope to see you all tomorrow again.